Okay, great. So maybe we can get started. Before Professor Xu's talk, I'd like to introduce Professor Xu briefly in Chinese.
Okay, good.
徐教授他是密歇根州立，目前是密歇根州立大学的这个教授，博士生导师，曾经担任过密歇根州立大学的这个副校长。那么在教职之前，他曾经也担任过哈佛大学那个特别的那种研究员，以及超导超级对撞机项目组的一个成员，并在耶鲁大学和这个Oregon 大学这个担任教职，后来就是说，之所以离开这个 Oregon， 就是去这个密歇根州立大学做副校长，所以说他就去了密歇根州立大学。那么徐教授他在粒子物理啊、宇宙学、还有量子场论、黑洞物理以及这个计算基因组学方面有非常深厚的这个造诣，发表论文180余篇。涵盖量子色动力学、暗能量、黑洞熵界线以及标准模型之外的粒子物理。我早期知道那个徐教授的这个工作就是关于暗能量，还有黑洞以及熵界的工作。但是徐老师在标准模型的之外的一些粒子物理，我因为和我的专业不是特别那个，我了解的不多。但是对徐老师做的这个暗能量呀、黑洞还有熵界的工作，我以前是在我做学生的时候是读过他的这个paper。那么同时还涉足这个基因组学、生物信息学以及现代金融啊，还有信息安全。特别现在徐教授也是对这个 AI 也是特别的感兴趣。当然，他也创立了多家的科技公司。这里我就具体我不了解这些科技公司，我就不说了。那么非常这个，今天我们非常荣幸能够请到那个徐教授讲他在这个黑洞物理，特别是和黑洞信息应用相关的这个工作，让我们大家欢迎。好。
Thank you very much. Should I use this mic or I'm okay? Okay. I'm very happy to be here. I'm sorry I have to give this lecture in English. My Chinese is not very good. I was born in the United States. My father, so when people see my last name, they sometimes think I'm from Taiwan. But actually, my father went to school in China. He's from Zhejiang. And he attended college at Tsinghua, but during the war. So he was in Kunming during the Second World War as a student. And then he came to the United States for graduate school to do his PhD in 1948. So before the communists won the war. And in 1948, our name was translated into English this way, even though today it would be XU. So anyway, that's my family has been in the United States a long time, and that's why my Chinese is not good enough to give the talk in Chinese, so I have to give it in English. But I will try to speak in a slow, accessible way, and I hope you enjoy the talk. Feel free to ask questions at any time, okay? So if you have a question, just raise your hand. If you're a student, there's no such thing as a dumb question or a bad question. Just ask the question, okay? So please. Yeah, go ahead.
So you say your father just studied at Kunming during World War.
Yeah.
At that time, I guess C.N. Yang and TTV.
Yes, they were. So my father's field is aerospace engineering.
Oh.
And so they were on campus at the same time, but he was not a physics major.
I see.
Yeah. Yeah. Okay, but in the talk, please, if you're a student and you're confused about something, just ask a question. We have plenty of time. And I enjoy questions. So the more questions people ask, the more fun the talk is for me. So please ask questions. Okay, so this talk is mostly about, is this a pointer also, or? Yeah, okay. This talk is mostly about the work done in this recent paper, but I will also talk about related work in some earlier papers. Most of the work is done with my collaborator, Xavier Calmet, who's a professor in the University of Sussex in England. For students, these are good review articles on this topic, which I recommend. So the topics that I discuss are discussed in a pedagogical way in these review articles. Okay, now I'm going to be talking about the information paradox. This is something that has been an open problem now for almost 50 years. So Hawking first pointed out that there is this conflict between general relativity and quantum mechanics, and he pointed it out almost 50 years ago. And some people think that we can't solve this problem because we don't fully understand quantum gravity. But one of the points I want to make is that this problem, this Hawking information paradox, is a long-distance property of gravity. It's a property of gravity not at the shortest distance scales, but on very, very large distance scales. And we think we actually understand gravity on those length scales. So that's why this paradox or this information problem has been so challenging for so long. Now, here I have more and more sophisticated theories of gravity. So starting very simply with Newtonian gravity or general relativity. Once you have general relativity and you add quantum fields, so you treat gravity classically, but you add some quantum fields, then already you can deduce the Hawking paradox. You can conclude that black holes evaporate and that there's some problem with how the information that is inside the black hole comes out. So that's already available to you at this level of sophistication. If we just go one step further and we just quantize the gravity field, we quantize the graviton, but we only consider long distance excitations of the graviton, I claim we can make some significant progress towards solving this problem. And so that's what this talk will be about. Okay, so here's an outline. I'm going to review the basic physics of black hole evaporation. So if you're a student and you don't have a good grasp of this, I will give a very, very accessible picture of how black holes evaporate and how to think physically about what is happening. I will then discuss some recent work using something called replica wormholes to reproduce something called the page curve. I'll explain what all these things are. The part of this work that I want to emphasize, this is relatively recent work. This is work from just a few years ago. The part of this that I want to emphasize is the physical nature of the final radiation state. So after the black hole is almost completely gone and almost all of its energy is in radiation, so heading away to infinity, we can ask what is the physical nature of this radiation state? And I claim that we can conclude that it is actually a macroscopic superposition state. It is a superposition of many, many different states, and those states have macroscopically different properties from each other. So that's what I'll emphasize in the second part of the talk. In the third part of the talk, I will show that this property in part 2 invalidates certain results, something called Matour's theorem, which is used to describe the Hawking information paradox, and something else called firewalls. And this observation actually invalidates these previous results. And then finally, I'm going to talk about a physical picture which emerges not in Euclidean space. So in Euclidean space, we have imaginary time. But if we have real time, there's another way to derive this conclusion about macroscopic superposition states. And that comes from something called quantum hair. So quantum hair refers to quantum effects which appear outside the horizon of the black hole, but they're sensitive to the interior state of the black hole. And most of the earlier papers that I listed on the first slide are papers in which we derive the existence of quantum hair. We show that there are quantum effects outside the black hole that are sensitive to the state inside the black hole. And we also show in some of those papers that external quantum set of external quantum effects, which we call quantum hair, actually affect Hawking amplitudes. So they change the Hawking amplitudes. And so we actually have a whole framework where you can show that the actual Hawking amplitudes that cause the evaporation of the black hole are sensitive to the internal state. And that actually isn't true in the Hawking approximation. So in the Hawking approximation, he never treats the gravity field as quantum mechanical. But once you start treating it as quantum mechanical, you see that this is possible. Okay? So that's the outline of my talk. Okay? So let me now just introduce the physics of black holes, or the physics of evaporation of black holes, in the simplest possible way. So the first property we want to talk about is the nature of the light cone. So we know that in space-time, the future of this point, the future that can be causally influenced by this point, is contained inside of this future light cone. And the most important property of a black hole space-time is that the light cone tips over when you cross the horizon. Precisely when you cross the horizon, in fact, that's how we define the horizon, the light cone tips over so that the parts of the space-time that can be influenced by a particle here are all inside the black hole. And things which are outside the black hole can no longer be influenced by things which are behind the horizon. And this is the fundamental property of black holes, and from this property we deduce all the important consequences. Okay, so this is a cartoon picture of Hawking radiation and black hole evaporation. And of course, it's very simple compared to the really complicated methods that are used to derive Hawking radiation or to study evaporation of a black hole. But I claim this basic physical picture is correct. It captures the main points. And so let's suppose that we're sitting very close to the horizon of the black hole, just outside the black hole. If the black hole is very big, and we'll always talk about, in this lecture, we'll always talk about very big black holes. When you have a very big black hole, the curvature near the horizon, the space-time curvature, is small. It can be made arbitrarily small as I make the black hole bigger and bigger. And so the space-time very close to the horizon is very close to the flat space. It's very close to flat space. And the ground state of the quantum field near the horizon is essentially the ground state, the flat space vacuum. Okay? So we can imagine fluctuations in this vacuum. Those fluctuations have to have the same quantum numbers as the vacuum. So zero charge, zero angular momentum, etc. You can imagine, though, fluctuations in which, for example, you might have an E plus E minus pair, and one of the particles falls behind the horizon, and once it's behind the horizon, it will never reemerge. But the particle it is paired with in the fluctuation manages to escape to infinity. And it is the particle that escapes to infinity, which is the Hawking radiation. This particle enters the black hole carrying negative energy, and it causes the black hole to shrink slightly in size. These fluctuations are very rare, so they happen only very, very intermittently. It means the black hole evaporates very, very slowly. There is a temperature associated with the black hole. That temperature characterizes the wavelength or the energy of these fluctuations. And when you work this out in detail, you find the temperature goes like 1 over the radius of the black hole, or 1 over the mass of the black hole. So for very big black holes, this temperature is very low, and the wavelength of the excitations is about the same size as the black hole. So if you have a black hole which has a Schwarzschild radius of 100 kilometers, you're actually talking about 100 kilometer wavelength Hawking radiation. So very, very low energy excitations, and excitations that we should actually be able to understand using known physics. Okay? Now, what happens with the black hole is it sits there for a very long period of time, and then after a long time, maybe it emits one Hawking quantum. It loses a little bit of energy from that Hawking quantum, and it shrinks a little bit. Okay? But then it sits there for a very long time, A very long time elapses before it emits the next quantum. There's plenty of time for the vacuum state to relax to its lowest energy configuration. And then only after a long time does another Hawking quantum emerge. So we're talking about a very slow process involving very low energy excitations, a process which takes a very long time. So the lifetime of a black hole, the time it takes for all of the energy to evaporate, scales like the mass of the black hole cubed. When you have a very big black hole, that can be very long, it can be much longer than the age of the universe. Okay? So we're talking about physics that is low energy physics, long wavelength physics, very slow timescale physics, has nothing to do with ultraviolet physics. It has nothing to do with the Planck scale or fluctuations happening at the Planck scale. And it's very surprising that we can't understand this physics after 50 years. We still are confused about whether black hole, the information that's inside the black hole emerges in the Hawking radiation. Okay, so this is something called a Penrose diagram. Hopefully everybody's familiar with this. A set of special coordinate transformations has been made to represent an entire universe on this Penrose diagram. In the Penrose diagram, light moves along 45-degree angles. So if a photon is heading into the black hole, it's moving like this. If a photon is heading out to infinity, it's moving like this. Okay? What's shown here is a star or some kind of ball of dust or something which collapses into a black hole. Once the matter has collapsed far enough, a horizon forms. There is Hawking radiation emitted by the black hole. There is a singularity inside the black hole, at least in classical general relativity. But because the black hole evaporates, eventually there is no singularity and there's no horizon. Okay, so at late times there's no black hole. Okay? One physical way to understand this diagram is to look at this world line, this dotted line. This is a possible world line of an external observer. So you might be in a rocket ship, kind of hanging around, and watching the star, watching it collapse to a black hole, watching the black hole evaporate, and then after a while there's nothing left except the radiation that goes to infinity. Okay? And so on this world line, at point A, you could be sitting here in your rocket ship. You could receive a photon from the star. So you can know that there was once a star here. Okay? If you wait a little bit longer, if you go to point B on your world line, you can see that there is a black hole. You can maybe watch some probe fall into the black hole, or you can see the Hawking radiation come out of the black hole. And if you wait even longer to point C, you can see there is no black hole. It's fully evaporated. And all that's left is radiation that's heading towards scribe plus, toward infinity. Okay? So on this diagram, you can represent for a real physical observer all of the phenomena involved with the black hole. Collapse of an original object to form a black hole, evaporation of the black hole, and then a period of time when there's no black hole. And the question is whether the radiation, which is all that's left of the black hole at the end, can possibly reproduce all the information that's inside the matter that fell into the black hole. If that is not possible, what happens is that some information which was present here at early times in this universe is lost at late times. And so that is a paradox. If gravity forces information to be lost, then there is a problem. More technically, we could say it's possible that gravity caught, and this is what Hawking said in 1976, he said, it's possible that black holes, or he asserted that black holes cause pure states to evolve into mixed states. So a pure state at some early times might evolve into a mixed state at some later time. And that is a problem because that is not supposed to happen in quantum mechanics. Okay. One way to express the paradox is to foliate the space-time with space-like slices. Okay? So each of these blue lines could be considered one moment in time if you choose the right coordinate system. And you can ask questions like, what is the future evolution of the wave function or the state on this blue line to this blue line to this blue line to this blue line to this blue line. So you can ask, like, how does the state evolve? And is there some information that's on this state which is lost here, which does not reappear here? Okay. One particular thing you can do is you can look at something called a nice slice. You could look at this slice here. This slice intersects all the matter that fell into the black hole, and it intersects almost all of the Hawking radiation that comes out of the black hole. There's something called a no cloning theorem, which says the information that exists here cannot also exist here. And that's another way of expressing the paradox. Okay? All right. Now, this is something called the Page curve. So in the 1980s, someone named Don Page, who had been a student of Kip Thorne and was a postdoc with Hawking, asked the following question. Suppose the evaporation of the black hole is unitary. In other words, suppose that the final state of the radiation at the end is a pure state. Then you could deduce that the entanglement entropy of the radiation has to follow this shape. So what do we mean by the entanglement entropy of the radiation? So suppose you have this black hole and it's sending out radiation. You could compute the entanglement entropy of the radiation, which means you look at the density matrix describing the radiation itself. You trace over the degrees of freedom in the black hole, because eventually you lose that at the end of the day. You don't have the black hole anymore. So you define an entanglement entropy of the radiation, which is the trace of the density matrix of the radiation tracing over the degrees of freedom in the black hole. Okay? So that's what's plotted on the vertical axis. So entropy of the outgoing radiation. In the Hawking calculation, this entanglement entropy just goes up, 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 up. It goes monotonically up. Okay? It just keeps increasing. The reason it keeps increasing is because if you think of the Hawking radiation as starting with a pair, some entangled pair that has the same quantum numbers as the vacuum state, one of the particles falls in and the other one becomes the Hawking radiation, but these two are entangled with each other. So if you force me to trace over this degree of freedom, the resulting entanglement entropy always goes up. Every time I produce a Hawking pair, I later only have access to one, so the entanglement entropy has to just keep going up. Every time I emit something from the black hole, the entanglement entropy of the outgoing radiation goes up. Okay? So if that if that picture of what's happening is true, then you must get this kind of green line. Okay? And that's why Hawking said there is a problem, because we could start out with a pure state, collapse it into a black hole. At the end, we get this radiation, but the radiation has a very high entropy and is in a mixed state. So how can a pure state evolve into a mixed state? That contradicts what we expect from quantum mechanics. Okay? What Don Page did was compute specifically what happens if we require that the final state actually be a pure state. So that means that the entanglement entropy goes up, at least initially, but at some point it has to turn over because it has to eventually head back down to zero. Okay? So people who claim that Hawking was incorrect and that there is a resolution or a solution of the black hole information problem, they have to explain why we get this curve, the one that goes up and down, instead of the green curve. Okay? And although Page pointed this out a long time ago, there was until recently no specific calculation which could reproduce this Page curve. And what happened recently is, in very specific models of quantum gravity, two-dimensional models of quantum gravity, they could actually reproduce the Page curve in the following sense. So they could show that there would be a special point in time after a certain amount of evaporation has occurred when emitting the next quantum from the black hole actually causes the entanglement entropy to go down instead of up. So they're able to reproduce this behavior, the turnover of the entropy function. Of course, nobody can go all the way to the end here, because at the end, you are talking about short distance physics, because when the black hole gets very, very small, the last few quanta that come out of the black hole are high frequency, even Planck energy particles. And so you can't really talk about the very end point of this evolution without some specific theory of quantum gravity, like string theory. But you could talk about most of this evolution on this diagram. I just want to emphasize how mysterious this point is. So imagine that I had a black hole which was 100 kilometers. The Schwarzschild radius was 100 kilometers, and half of it evaporates. So now the radius is, say, 50 kilometers, okay? Or still some macroscopic size. We would expect that the approximations that Hawking made would still be extremely good, right? So if half the mass of the black hole evaporates, we would expect, or even 9/10 of the mass of the black hole evaporates, we would still expect all of the approximations that Hawking made to be very accurate. So how could I be wrong by order 1 on the behavior of this? Why is it that when quantum gravity is still a very, very tiny correction to the physics, how could it be that even the sign of the change of this entanglement entropy is wrong? So Hawking's calculation says the delta, the change in this quantity is always positive, but somehow it became negative. What is it about our understanding of low energy physics that could explain this change? Okay, so that is a mystery. These replica wormhole calculations give a very explicit understanding of what is happening here. Okay, and so that's why they're important. Okay, so let me introduce the conceptually clearest way to think about the Hilbert space that we're dealing with here. Okay, so imagine a period of time after the black hole is completely gone, and all we have is some big shell of Hawking radiation which is heading toward infinity. Most of the modes in that shell are very low energy modes. Only a few at the very end are high energy modes. Okay? And so let's represent the first Hawking quantum that's emitted. Let's describe its quantum numbers by R1. The quantum numbers of the second Hawking quantum emitted are R2 and all the way up to N. And let's just assume they're exactly N quanta emitted when as this black hole evaporates. So after Rn, the black hole is gone. Okay. As I mentioned before, each of these quanta are typically very widely separated. There's a long period of time between emissions. Each of these is just a Fock state, F-O-C-K, Fock state, or perturbative excitation on a nearly flat background, right? Because once the black hole is gone, all I have is this stuff way out at infinity. It's widely separated. It can be thought of as just individual modes that are heading toward infinity. So this Hilbert space is very easy for us to understand. Okay, the Hilbert space itself is easy for us to understand. Of course, it's a very big Hilbert space because the set of possible configurations in here is exponentially large in the area of the black hole. Okay, so it's a very large Hilbert space, but it is easy to understand. There's nothing challenging about the physics of understanding this because it's representable as just a Fock state. Now, the first thing I want to point out is that even within this set of R1 through Rn, if I constrain the total energy to be the total mass of the black hole, I constrain the total charge to be the original charge of the black hole, all of the conserved quantum numbers, I impose those constraints on this. After I do that, all possible states in this Hilbert space, so once I impose those constraints, all possible states in that Hilbert space are possible. And so the most general state that you get from the evaporation of the black hole, it could be in principle a superposition of many different possible things which live in that Hilbert space. And in particular, if you think about it, each of the emissions is close to thermal. In the Hawking approximation, each one looks like for example, the distribution of energies or distribution of momenta looks like something that's coming from a hot object of temperature T. So we know that there's lots of variety. The quantum could come out like this, it could come out like this, it could be an electron, it could be a photon, it could have charge Q, it could have charge minus Q. There are many, many different possibilities, and some of those possibilities are macroscopically different from others. So I could have a little patch here of positive charge, which is going out. or instead, in some other possibility, I could have a little patch of negative charge, which is coming out like this. So there are macroscopically different possibilities, and generically, we have to think in terms of possibly a superposition of all those different things. Okay, so that's an important conceptual point that I want to make. Now, I don't know if you can read the top there, but the reason I first introduced this discussion in terms of the Fock space is so that you have a very clear understanding of what is going on, just in terms of the radiation. But now we can ask a more interesting question. What is the black hole doing while this information is being emitted? Because of conservation of energy and momentum, if I have a bunch of particles that come out like this, the black hole will recoil in the opposite direction. If I have an excess of particles going like this, the black hole will recoil in this direction. So if I follow the black hole instead of the radiation pattern, I see that for each choice of this radiation pattern, I get a specific recoil trajectory of the black hole. And there are exponentially many different recoil trajectories of the black hole. So the dimensionality of this Hilbert space is e to the area of the black hole, and also the set of possible recoil trajectories is also exponentially large. Okay?
So here I have
yeah.
Why you claim this is exponentially large?
So it's the dimensionality of the Hilbert space, right? So that is actually the entropy,
Sure.
right? So and the entropy is so the entropy is the area of the black hole. Right? So the dimensionality of this Hilbert space has to be e to the a, actually.
Okay, I see.
Yeah. This has actually been studied in very great detail. So like people have actually looked at, let's say you just assume the Hawking result for the thermal emission of the quanta, and you just follow the black hole as it emits the quanta, and you just calculate the statistical entropy of all the possible radiation states, and you get basically something like the area. You don't necessarily get a over 4, but you get something like the area. But then you know the dimensionality of that Hilbert space is e to the a. Okay? And once you know the dimensionality of the Fock space, Hilbert space is e to the a, then you know the set of possible trajectories, recoil trajectories, is also exponentially large. Okay? So I went through all this discussion to make it clear to you that we are actually talking about distinct space-time geometries here. So when you make that Penrose diagram, by convention, we always put the black hole at the origin. We have the black hole at r equals 0 on the Penrose diagram. And we have to make a bunch of coordinate transformations for that to be true. The set of coordinate transformations I have to make to put this black hole at the origin is different from the ones that I used to put this black hole at the origin. So each Penrose diagram, and there are exponentially many of them, corresponds to a different set of coordinate transformations relative to another one. Okay? So naively, when we just think about the paradox, in the earlier formulations of the paradox, I said, oh, just take this one Penrose diagram and make some nice slices on the Penrose diagram. That's very misleading because now I've pointed out to you that they're actually an exponentially large set of Penrose diagrams that are involved in this process, and they're all different from each other. Okay, so that's the main physical point that I want to emphasize. If that's not clear, please ask a question. Or any question? No. Okay. So yeah.
I think the Penrose diagram is a classical concept. Why use the different microstate where it
Good. Great question. So the Penrose diagram is a classical concept, but if you looked at how we formulated the paradox, we were using that Penrose diagram in a context. We were talking about pure states, mixed states, quantum particles propagating to infinity, right? So we were mixing these concepts. Initially, are you trying to move the bar?
Yeah.
Okay.
Learn how to keep this current.
You could just leave it like that. I think it'll be okay.
Always.
升起来。然后鼠标一开一开。
It's all right. I'll read you what's up there, so in case you can't see it. So back to your question. So initially, what Hawking does in his calculations, he has a classical space-time, and he just computes some things about quantum fields on that space-time. Even the shrinking of the black hole, which we call the back reaction of the black hole, people actually cannot really, until some more recent work by Parikh and Wilczek, people could not really explain like what is the back reaction of the black hole. We just assume that there's back reaction because of energy conservation and momentum conservation. But when people try to formulate the information paradox, they're mixing quantum and classical. Because even that diagram, I don't want to go backwards because I think there's a little problem when we go back. I can go back? Okay. Okay, I can go back. Yeah, so even this diagram mixes quantum and classical because what makes this black hole disappear? The only reason this black hole disappears is because somehow we're imposing by hand this back reaction property. And then after a while, there's no energy left in the black hole and it doesn't exist anymore, right? So already this space-time diagram is kind of using side information, which isn't just a purely classical treatment of gravity. We've imposed that back reaction, we've imposed energy conservation, and the energy conservation is in response to quantum particles that are being emitted. So this is already some kind of hybrid representation of the physical situation. Okay, so instead of thinking of this diagram, I would say just think in terms of a black hole. The black hole is some compact object. It's emitting quantum particles. It has to, because of conservation of momentum, it has to react to those particles. So clearly you have some really complicated situation. And if you try to connect back to the usual treatments of this problem, you realize there are many different actual situations that you have to deal with.
Yeah, but I think the different microstates in classically is the same Penrose diagram, but I think different is we have different quantum field state in the next slides.
So, in this diagram, you're hiding the set of coordinate transformations that you always do to put the black hole at r equals 0. So you can imagine just like take two circumstances. So in one circumstance, the quantum comes out like this and the black hole does this, and the other one like this. So already there, I actually have two different situations. One, the black hole is at coordinate x1, and the other one it's at x2. Okay, so already there you can tell there are two Penrose diagrams we could talk about because there are two different sets of coordinate transformations I have to do to put the black hole back at r equals 0.
My opinion is that if we treat the Penrose diagram as a classical approximation, maybe say if in the case 1 we evaporate spin up.
Yes.
And in case 2 we evaporate spin down.
Yep.
Then we can say there are two nice slides in the same Penrose diagram. The first nice slide describes the spin up. The second describes the spin down. So in this situation, I think we can describe in the same.
Well, so in the case where, well, so spin is a little bit tricky, okay, because then we have to talk about the angular momentum of the black hole. But let's talk about the momentum of the Hawking quantum that's emitted. Yeah. Okay, so clearly you can have situations where the black hole is mainly recoiling to the left, and you can have a case where the same black hole at the same period of time is, because of some other amplitude, is recoiling to the right. And there's clearly no way that I can represent both of those things on the same Penrose diagram. Yeah.
But if we think the two processes in microscopic, microscopic thing is the same, and the geometry, you cannot always evaporate a particle, its momentum is left. Because if you evaporate, say, 1 billion particle, its momentum is always left, and another case is 1 million particle always the right. They are classically very different. So
They are classical. That's the whole point, yes. So there's another paper by Page, which was written about the same time as when he wrote the Page curve paper, in which he points out that the variance, so if you take the variance in the location of the black hole as it evaporates, so the expectation value of delta x squared, where x is the coordinate of the black hole, that grows like m squared. Okay, so m is in Planck units is very large. There turns out there's an astronomical, almost even cosmological uncertainty in the location of the black hole by the time half of it has evaporated. So that was known, at least to some people, for a long time, but most people don't realize this. So the idea that I could have, say the black hole, say our sun turns into a black hole and starts evaporating, and by the time half of it has evaporated, one particular trajectory has the black hole out near Pluto, and the other trajectory has it near Mars. Okay? Clearly, those are not the same Penrose diagram, right? So, yeah. So, my only point is that we have to consider that in the discussion of the evaporation process. It's an exponentially rich set of different states, and they're actually different space-time backgrounds that you're talking about, okay? Now, earlier I said, when this curve turns over, our low energy approximations should still be very good. So what large effect could cause this order 1 correction in the Page curve? And the answer that I'm going to give you is that once you realize there's this exponentially rich set of space-time backgrounds or states that you have to consider, entanglement between them becomes an important aspect of the problem. But if you always only consider one Penrose diagram, you just consider what's happening on that diagram, you neglect entanglement between that specific state and these exponentially large set of other states. So that's where I'm going with all this. Okay.
So,
yes?
So here I want to sharpen the question asked by so actually somehow you attribute the exponentially many states just to the Penrose diagram with different origin, with just this kind of exponentially many states are just characterized by some kind of coordinate transformation.
Yeah.
So I guess this may not be true. So suppose now I just have a black hole sitting at the origin. So okay, just by Hawking formula we know actually we have exponentially many microscopic states just with same position at the origin.
Yes, yes.
But so I guess
this
is your question,
right?
This
is my question.
Yeah.
So maybe you're asking me what are the physical microstates that correspond to the area entropy of the black hole? Is that what you're asking me?
Yeah.
So that's a slightly different question than if half of it evaporates, okay, what are the different physical trajectories that the black hole could take? Because you still have, in this setup, you still have half the black hole left. There's still a bunch of internal microstates of that black hole. But of course, the area maybe went down by a factor of 2 or something, or factor of 4 or whatever. Where is that information? And could it be in the radiation? But by conservation of energy and momentum, it's also reflected in the recoil trajectory of the physical black hole. Okay. I actually want to say that the Penrose diagram is actually very misleading. It actually has misled people for about 50 years. I think so I was a student of Richard Feynman, okay? So Feynman has a very physical way of thinking. If you talk to Feynman, he would say, well, forget about this. I mean, this is crazy. You're making these, you've basically taken a 3 + 1 dimensional space and you're trying to represent it in 2 dimensions. And there's so much hidden information in that Penrose diagram. He would just say, forget about it, okay? You know you have a black hole. You know energy and momentum are conserved. If you suddenly say energy and momentum are not conserved, you have bigger problems than the Hawking problem, okay? So you have a thing. The thing is emitting particles every now and then, and it's random walking in response to those emissions. So if quantum mechanics holds throughout the whole discussion, which is the whole question here, then you must end up with a superposition state with radically different recoil trajectories. That's actually all I'm saying. It's a pretty trivial point, but it's an important conceptual point because it's been obscured in the field for a long time, actually.
But here the exponential embedding is important.
It is important. We'll get to this. We're going to do some math now. The exponentially large dimensionality of the Hilbert space will be important now. Okay.
However,
Yeah.
the radiation patterns here seems like a quantum description. Yes. But the position of black hole we often talk about, it must be a classical description. So you cannot combine a quantum description with a.
Yes, I understand your question. So imagine that I have a box, and in the box there's some particles, like air particles. And suppose the big object in the box is maybe a seed from a plant, and I'm looking at it under a microscope. Okay? So what I've just described to you is Brownian motion. Do you know Brownian motion? Okay, so I can have a macroscopic particle interacting with microscopic particles, which I cannot see, and the interaction of them causes the macroscopic particle to random walk. There is still a quantum mechanical description of the macroscopic particle. We're just not used to using it. Okay? But so we describe it as, oh yeah, the seed, the thing I'm looking at, has a classical location, but it actually has a wave function. Okay? And in fact, even that system, this is a different question, but even that system you can show evolves into a macroscopic superposition state. But we can talk about that separately. But the point is, like, the black hole itself, if you look at the center of mass coordinate of the black hole, that is a degree of freedom in the system, and it has to have a quantum description. Okay, even though it's to a good approximation, we can pretend it's classical, but actually at the most fundamental level, it has a quantum description. And it's exactly like Brownian motion. Okay. Okay, so here's just a list of the points that I've tried to make. So if Hawking radiation amplitudes are, well, okay, so this is something I'm going to get to later, but if they are weakly dependent on the internal state of the black hole, then you will get entanglement between states representing different radiation patterns. That implies entanglement between states representing different recoil trajectories, and that implies entanglement across semi-classical spacetimes, which describe different recoil trajectories. So this is just, in a way, a kind of summary of what I've been saying. Okay, this is something I'll get to later. Okay, all right. So now let's do a little bit of math, okay? So what this says is density matrix of radiation state, okay? This is a calculation that is very old. It was done in like about 2013. There's a paper by Raju and Papadodimas, and also a paper by me. And the question is the following. Suppose I give you a density matrix, and suppose the density matrix is maximally mixed. So it's proportional to the identity matrix. And 1 over d here is the dimensionality of the spacetime. Okay, this is the thing which is exponentially large. It's like e to the a or something. Okay. And in the replica wormhole calculation, you actually get this from, if you take the Gibbons-Hawking saddlepoint in the path integral. I'll talk about this in a minute. Okay. But in this old calculation, you can ask the following question. Suppose that there are some small corrections to this originally maximally mixed description. And let's suppose that we look at the purity of this density matrix, which is the trace of rho squared. So trace of rho squared is 1 if it's a pure state. For this guy, you can see trace of rho squared is 1 over d. Okay, because when I square it, I get d to the minus 2. The square of the identity matrix is the identity matrix. I take the trace, I get 1 power of d, but the purity is very small. It's 1 over d. Okay, so this is a configuration which is mixed, very impure. The question is, what types of perturbations, delta rho, could restore purity to this state? So it's a very general question. It does not, at this point, you don't even have to think about black holes. You can just say, I gave you a density matrix, it's maximally mixed, but now I'm going to write some perturbations to it, which I call delta rho. What types of perturbations could restore purity to my state? Okay? This is also related to the question of if I have a state which is really complex and it's a pure state, how hard is it to tell whether it's a pure state or a mixed state? Do I have to measure all possible entries of the density matrix, or can I just measure some entries and conclude that it's a pure state or a mixed state? So there's a very specific problem in quantum statistical mechanics here that this is related to. Okay. Now, a reasonable ansatz for this delta rho in the case of quantum gravity is that I could write for delta rho some small corrections, and those corrections should be very small. So we're going to say they're characterized by some parameter x, and x is really small. X could be e to the minus the area of the black hole. So those could be non-perturbative string theory corrections, whatever you want. Very small corrections, okay? But let's assume that the matrix form of delta rho is non-sparse. What do we mean by non-sparse? We mean almost every entry is non-zero, okay? So physically, that means that there is widespread entanglement, okay? And if we're talking about the Hilbert space of radiation states, we are saying, well, let's choose an ansatz where there's widespread entanglement between all of these radiation states, okay? So non-perturbatively small corrections, but spread over this huge Hilbert space. Could that purify a maximally mixed density matrix? And the answer is yes. So surprisingly, the answer is yes. And this has been known for a long time. So because we assumed it was non-sparse, when we compute delta rho squared, okay, so now when I add this perturbation and I compute trace rho squared, there's a piece of it which looks like this, trace of delta rho squared. Because every entry is populated, when I take one of the rows and one of the columns, delta rho times delta rho, I actually get of order d non-zero terms. So I get a power of d in the numerator upstairs. And this is the key point, okay? So if entanglement is widespread enough, I can get a power of d upstairs. And when I compute trace of delta rho squared, I can get an answer which is as large as x squared. Okay? So each entry of the matrix is of order x. I multiply the matrix by itself. The one of the powers of 1 over d is canceled. And so I could get, for the purity, I could get something as large as x squared. Okay? So this is very, very simple mathematically. There's nothing complicated here mathematically. Physically, though, the important point is you could have non-perturbatively small corrections, but if there are enough of those corrections and they're spread out in this very, very large Hilbert space, they could cause a significant change, qualitative change. And I claim that is actually the mechanism in the replica wormhole calculation that causes the page curve to turn over. Question? Yeah?
How small is x here?
I'm going to talk about that. Okay, it's non-perturbatively small. Okay, so let's go back to the page curve. Now, in the page curve, I'm talking about the entanglement entropy, which is not the same as the purity. When you talk about purity, the mixed state has low purity, and you're trying to get back up to 1. Okay? But when the perturbation starts to be as large as a leading order piece, that's when you get this turnover from the green line to the blue line. Okay, so that's what we're talking about here. So at leading order, the purity is of order 1 over the dimensionality of the Hilbert space. The correction could be as large, if we assume very broad entanglement, the correction could be as large as this non-perturbative scale squared. Okay? What's a plausible form for this non-perturbative effect? We could say it's e to the minus some constant times the entropy of the black hole. Okay? When the black hole is really big, x is really small. As the black hole gets smaller, the suppression factor gets weaker, and so x is actually increasing in time. Okay? When I get finally to a Planckian black hole, these could be order 1 corrections. Okay? In the middle, they're still quite small. The dimensionality of this radiation space is also e to the e to the entropy of the black hole. Okay? This d inverse is decreasing in time. Okay? Because the Hilbert space is getting bigger and bigger, and 1 over d is getting smaller and smaller. Okay? So I have a situation where I compare the correction, which is x squared, to the leading order term, which is d inverse, and these two will actually cross because x is increasing in time The leading order piece is decreasing in time. And where they cross is exactly where this happens. Okay? So we have an effect where we say, we didn't really realize there was such a big Hilbert space involved here. Okay, when we consider that and we consider the possibility that there's uniform widespread entanglement in this Hilbert space, we can reach a conclusion where even though the corrections x are always exponentially small, they can overwhelm the leading order contribution, and they can cause the green line to become the blue line. Okay, so that's the key point. Okay?
I see.
Yeah.
I understand the form of x.
Yes.
Is that just an assumption or?
So in 2013, when Raju and Papadimos and I wrote papers on this, we had no idea what these effects were. We just said, for sure, in the Hawking calculation, if there is some non-perturbative quantum gravity effect, it's not been included in the calculation. So for sure, we expect some corrections which could be e to the minus area of the black hole. Corrections that small. Okay? So at that time, it was just purely speculative. At this point in the replica models, I'll tell you what x is. X is the extra action in the throat of the wormhole. And it is exponential in the area of the black hole. So all these questions are answered explicitly in those models. Okay? But at the time when this analysis was first done, we didn't know what x would be. Okay. Okay, so let's talk about the replica wormhole calculation. So I start with a two-dimensional theory of quantum gravity. They're doing something more ambitious, which is they're trying to compute trace of rho to an arbitrary power k. And then they take the limit as k goes to 0. That's the replica trick. Let me today only talk about the purity. I'm only going to talk about the purity because that's what we've been analyzing. Okay? In their method to compute the purity, there is a leading order contribution, and then there's a correction due to wormholes. Leading order contribution is 2 copies of the Gibbons-Hawking black hole. So we go from real time to imaginary time. There's a conical singularity here. The radius of this black hole has to be quantized. This black hole configuration has to be quantized, and it basically ends up being 1 over the temperature. Okay, so that's pretty familiar. If you don't let these 2 copies, so these 2 copies appear in the Euclidean path integral expression for this quantity. So they have a way of representing trace of rho to the k in terms of a path integral, and then they dominate that path integral with some classical configurations. The leading order piece, which reproduces all the Hawking results, is 2 copies of a Gibbons-Hawking black hole in the path integral. Okay, so that part's quite old. The new part is they realized they could find classical solutions in which the interior of the 2 black holes, you have 2 black holes here, but you connect the interior with the wormhole. This configuration has higher action than this one. And so that action causes this to be suppressed by e to the minus some coefficient times the area of the black hole. Okay? So it's just like what we had before. If you compute trace rho squared using just this piece, you get 1 over d. If you compute it using this, you get 1 over d times some exponentially small thing. Okay, so it's exactly a realization of the more general analysis that I just gave. Okay. Okay, so I don't want to talk about their calculation. It's very specific to the low-dimensional model that they're working in. But the key point here is that in my calculation, in order to get something interesting, I had to assert that entanglement was widespread, that basically these entries x were everywhere in the density matrix. What's the analog in their calculation? The analog in their calculation is that when they compute the wormhole piece, there is a combinatorial factor. There are d times as many wormhole configurations as there are Gibbons-Hawking configurations. So even though the wormhole contribution is down by e to the minus area of the black hole, there are d times as many of them. Okay? And so it is, again, a competition between an extra power of d and that exponential suppression. And that's exactly what comes out of their calculation. Okay? In their calculation, these labels ij are the basis states for the radiation space. In this diagrammatic language, they get an extra trace or sum over one of the values of I or j. And so they get an extra power of d in the calculation. Okay, so this is what I just said. So there's a combinatorial property that allows the wormhole configurations to dominate the path integral at large d. So the wormhole configuration, a single wormhole configuration is always x times smaller than the leading order piece, but there are d times as many of them. So it's exactly the same competition that I talked about. So if you go very late in the evaporation process where d gets very large and the area of the black hole is shrinking, then you can have the second order, the correction dominate the leading order piece. And that is exactly where the page curve turns over. Okay, so the physical thing that's going on here, if you come back to my language of, well, we could think of it in terms of recoil trajectories of the black hole. There are many different recoil trajectories. The wormhole can connect any two of those black holes. So if I had one black hole that did this and another one that did this, they have different locations, they have different velocities. But it's a weird property of general relativity that I can connect the interiors of those two black holes. And the action that I have to pay is the same, regardless of which trajectory this hole is on and which trajectory this hole is on. So here's a bad picture of this. So I really have two universes. I have one universe where this guy has undergone his recoil trajectory. I have another universe where this guy has undergone his recoil trajectory, and then there's a wormhole connecting them. But what's interesting is these wormhole solutions, the action of these wormhole solutions is independent of x1 minus x2. And they're independent of the velocity of these. Because all I'm really doing is I'm attaching a tube to the interior of the hole. And all it cares about is the field at that point and maybe its derivatives in the interior. It doesn't care where the interior is in the first universe or where it is in the second universe. It doesn't care what the recoil velocity is. Okay? So that, in my entanglement language, that means any two of these recoil trajectories gets about the same amount of entanglement from this wormhole effect. Okay? So semi-classical geometry of the black hole interior doesn't really depend on the trajectory that it's taken. And so the properties of this wormhole connecting the two doesn't depend on it. And that's what's found in their calculation. Okay? All right. This is from our paper. This is what we say about this. But I've already said it in words. So let me just skip that. Okay. Sorry. But let me just emphasize, just review what we've talked about. So I said, when you consider the full Hilbert space of what's happening here, it's a very large Hilbert space. There are many different recoil trajectories. In general, if there were a maximal amount of entanglement between these different trajectories, then you could have an effect which, even though quantum gravity is still a small correction, so x is still exponentially small, this factor that can appear in the numerator can allow the correction to dominate the leading order piece, and that can allow the page curve to turn over. And that is exactly what is realized in the replica calculation. Okay? But if you turn it around and you say, well, let me look at the density matrix that you get from the replica calculation, you can see explicitly in that particular model that at late times, rho, the density matrix of the radiation, approaches this maximally entangled state that I described. So even macroscopically different patterns of radiation, which correspond to macroscopically different recoil trajectories of the black hole, are strongly entangled with each other. Okay, so that's an output of their calculation. Okay? Any questions about that? Yes?
So how can you use the Euclidean path integral to describe the black hole interior?
Interior? Yeah, so...
the Euclidean black hole, it has no internal.
Yeah, so So this is an analytic continuation of the, let's just say, the Schwarzschild black hole. So let's suppose you start with the Schwarzschild metric, but you continue to imaginary time. Okay? That gives you the Gibbons-Hawking, you could call it the Gibbons-Hawking instanton if you want. Okay? Because it's now Euclidean spacetime. So it's a gravitational instanton. Okay? And there is a description of what is happening, for small values of the radial coordinate. So there is something there. Now, what's happening here in these wormhole solutions is something non-trivial is happening here, where you're leaving the universe and you're connecting to you're connecting the two interiors of these two Gibbons-Hawking instantons. So it's very, if you look at these papers, it's very explicit. Now, because it's low dimensional, you're just talking about simple functions. So you just have some simple functions that interpolate here. Did I answer your question?
What do you mean by interior?
Yeah.
Just like the left figure, the tip of the figure, the tip of the cigar.
Yes.
It is the location of the horizon in the Lorentz black hole.
Yeah.
So in this figure, there seems like no black hole internal.
Correct.
No interior.
Yeah, no, that's a good point. So yes, this is no longer there.
So how you could use the Euclidean path theory to describe the wormhole to connect the two internal states?
Yeah. So what's really happening here is in this low dimensional theory of gravity, each I and J, I guess I should go to the other. Oh, I have I and J there. Okay. So I and J are labels on the Hilbert space of for example, the radiation that goes out. So there's some density matrix of that radiation. I'm trying to compute trace rho to the power k. Okay. For a given choice of I or J, that defines some boundary conditions at infinity. But then I look for a classical solution that obeys those boundary conditions. And the question is, can I find one that actually connects like this? It doesn't have to actually have this point anymore. But what's important is what's fixed here is I and J. The boundary conditions at infinity are fixed. But what quantum gravity or what the metric does in the middle is dynamical. I have to solve some Einstein equations to figure out what it's doing. And so they were able to find solutions like this that do that. Okay? But the key thing is, it's a good question, because the key thing here is the I's and J's. I'm trying to compute trace of rho times rho. And so I have to have a way of, for a given I and a given J, computing this saddle point of the path integral. But the interior, you're not constraining. That's determined dynamically. Okay. Okay. All right. Now, I have a few slides here. I don't know if I should go through this in detail because it really depends on how familiar you are with these particular results. But maybe let me go through this one. And I'm trying to explain here why this, quote, proof of an information paradox no longer holds once you become aware that you have to deal with entanglement across different macroscopic spacetimes. Okay? So this is the Matur theorem. So he says, let's describe the state of the black hole. This is the state of the interior of the black hole. And these are different Hawking pairs. These all have the same quantum numbers as the vacuum. So there's some highly entangled state. Now, this isn't a full description. This is some kind of caricature where this is some kind of EPR state, another EPR state, another EPR state. And one of these goes off. I think it's the B modes are assumed to escape to infinity, and you are required to trace eventually over the E modes. Okay? And so what Matur says is he says, well, because a long period of time elapses between when you emitted the first quantum, and then after a very long time you emitted the second quantum, et cetera, and a very long time you emitted the nth quantum. We know this vacuum state very well, so we could write down it's got to be some kind of EPR state. And there's no avoiding that the entanglement entropy just goes up by log 2. Because if you force me to trace over the state of the mode that fell in at the end of the calculation, I always get log 2 because it was entangled with something else and that something else fell into the black hole. Okay? So his claim is that if what we know about general relativity stays true throughout this evaporation. There's no avoiding this monotonic growth of the entanglement entropy. Okay? The problem with this is that if you look at this calculation, it is specific to one background geometry. The E and B modes that he's talking about are defined with respect to that background geometry. But if someone comes along later and says, well, there's actually some kind of much larger space of possibilities, in addition to this black hole, there's some other black hole over here, which also has this pattern, but there could be entanglement like this, okay? Not between these modes. So he allows for small perturbations where you modify this state a little bit, you modify this state a little bit, you modify this state a little bit. And that can, although that can change the log 2, the increase of log 2 each time you emit a mode, it's still some positive amount of entropy that's produced every time you emit a Hawking mode. But once you realize there's an exponentially large set of copies of this, and there's some entanglements possible between those different copies, then you can see this calculation doesn't actually tell you anything about what happens to the page curve. Okay? So I don't know if that's clear, but if you study this calculation, you realize, oh, he's actually assuming one spacetime throughout this entire calculation. You realize something is missing. Okay. Yeah.
How this calculation realize the A or 4G of the entropy? Because I can take any.
Say that. Sorry. Could you repeat your question?
How this calculate reproduce the entropy of A or 4G in the page transition point? Because it says I can take n to arbitrary.
So in this kind of tree, so this is not a very realistic description of the actual black hole evaporation. But let's suppose you do the following thing where you say, my first mode is going to have energy of order T. So 1 over, so the first mode is going to have, typical energy of order T, where T is the temperature of the black hole at that moment. But then as I emit more and more modes, the temperature is going up. And if you just sort of integrate dt over T, you actually can get something which is proportional to the area of the black hole. So this kind of treatment, even though it's just kind of approximate, you won't get A over 4. You can convince yourself that the amount of entropy that's released is of order A. Yeah. Yeah. Okay. All right. Should I talk about firewalls? How familiar are people with firewalls? Should I talk about? I could skip this. This is kind of specialized. There's a property called monogamy of entanglement, which is used in the firewall argument. Maybe let me not talk about this. If people have specific questions, I can come back to this later. But my only point here is that when you do the firewall construction, if you look carefully at it, you're always talking about one background spacetime. You're never allowing entanglement across these different spacetimes. But we just saw in the replica calculation that you have entanglement across these different spacetimes. Okay. Let me now switch gears and talk about something called quantum hair. Okay, so this is the subject of most of those papers that I showed you on the first slide. And the story goes like this. So imagine that you want to understand the quantum mechanics of very long wavelength gravitons. Okay, so we're not trying to do full-blown quantum gravity, we're not trying to do string theory, but we want to know if I have a 1 kilometer wavelength graviton and I scatter it off another 1 kilometer wavelength graviton, can I at least compute that? Okay? Or if I ask, what is the potential of some ball of mass here due to exchange of gravitons? What is the first correction to the classical potential? We know the classical potential, but we know there's some quantum corrections where we really treat, we treat fully gravitons of order, say, this length scale. In the calculation. What is the correction to the potential? Okay, so it turns out it's known how to do those things. And so what we did is we applied that specifically to the case of the exterior of a black hole. So you take these methods from low energy effective field theory for gravity, and then you ask, what are the corrections to the metric or the external gravitational field of a black hole. And you go ahead and compute those. Okay, so that's what we did. The effective action for quantum gravity is known. It's called the Vilkovitsky-DeWitt effective field theory. This has been known, I think, since the 80s. And the no-hair theorems do not apply to these effects because these are quantum mechanical effects. The no-hair theorems come from purely classical analysis of solutions of Einstein's equations. They don't really know anything about quantum mechanics, okay? And so the effects that we find are a kind of hair on black holes. So classically, you would say black holes have only limited kinds of hair, but the question is, when you turn on quantum mechanics, how much hair can black holes have? And so that's the question that we tried to address. I don't like this name, but we do refer to this stuff as quantum hair. And the interesting part is that this quantum hair actually affects the Hawking amplitudes. Okay? All right. So here's the example that we can really do explicit calculations in. So imagine you have a spherically symmetric pressureless dust ball. That's the simplest thing you can do. Okay? Pressureless dust collapsing to form a black hole. Okay? And we use this Vilkovitsky-DeWitt effective action to derive corrections to the evolution of that dust ball. In classical GR, you have something called Birkhoff's theorem. And because the dust ball is spherically symmetric, we know the external field of it can only depend on its total mass. Okay? The density profile, rho of r, the density profile of the dust ball does not come into the classical results. But we show actually that when you compute the quantum corrections do depend on rho of r. And in fact, you could in principle extract that entire rho of r by measuring things about the gravitational field of the object. So already at this stage, you can show there's infinitely more information available in the exterior state of the black hole than you would conclude based just on classical GR. Okay, so quantum hair contains infinitely more information than classical hair. Okay? Physically, what we're doing here, talking about low energy effective field theory, is very similar to a situation like this. So this is a baryon. I don't know if you guys study particle physics anymore, but this is a baryon with 3 quarks in it. And inside the baryon, you have these what are called valence quarks, but you also have lots of virtual fluctuations of quarks, and you have virtual fluctuations of gluons. It's actually a very complicated composite state. And you can ask, let's though suppose I want to probe this baryon. As I just said, the baryon is very complicated. It's got all kinds of fluctuations of charged degrees of freedom inside it. But let's suppose I want to probe this baryon with a very long wavelength photon. Let's suppose the wavelength of this photon is bigger than the baryon, and I want to probe the baryon with this photon. It's well known how to do this. The leading order coupling between the photon and the baryon is its total charge. Okay, even though it has this really complicated charge structure inside it, if I go to the long wavelength limit, I'm only going to couple to the total charge of the baryon. Okay. What's the analog for the gravitational field coupling to a black hole? So this black hole has a really complicated set of microstates. If I have a graviton field or gravity field coupling to it, what does it couple to? Well, we know it couples to the T mu nu of the black hole. So if I go to the rest frame of the black hole, it's coupling to the energy of the black hole. But what do we mean by the energy of the black hole? In classical general relativity, the energy or the mass of the black hole is a classical quantity. But in a fully quantum mechanical treatment where we say, oh, this black hole could have microstates, et cetera, this h mu nu would couple to the energy eigenvalue of the black hole. So if I just try to describe the black hole interior in terms of some states, and suppose I choose an energy basis, then there are very, very narrowly spaced energy eigenvalues. The splitting between those energy eigenvalues is something like, again, e to the minus a. And the external gravity field actually couples to those particular eigenvalues. Okay? So, So the point I'm trying to make is that the quantum hair we showed carries information about the internal state into the exterior of the black hole. And in particular, the quantum state of the gravity field knows about the specific energy eigenvalue of the microstate of the black hole. Okay, and that's in analogy to this example where in QED, you're just probing a baryon with the photon. Okay. This is the Vilkovitsky-DeWitt effective action. These are higher dimension operators which are induced by quantum effects. These coefficients C1, C2, C3, these are ultraviolet sensitive. So you don't know what C1, C2, C3 is unless you know what the short distance theory of gravity, like string theory, that you're trying to match to. However, there's a part of this action which is coming from infrared effects. It's coming from long wavelength virtual modes that we integrate out. And these alpha, beta, and gamma, these Wilson coefficients, they only depend on the massless particle content of the theory. So these are totally insensitive to whatever the short distance physics is. Okay? And the quantum hair that we compute is always due to these effects, alpha, beta, and gamma, and not to these effects, C1, C2, C3. So they do not depend on the UV completion of gravity. Okay? So coming back to this dust ball calculation, what we can do is we can modify the Einstein equations using these alpha, beta, gamma terms from the effective action. And when we resolve the perturbed Schrodinger equation, we get a modification to the space-time metric. We didn't write the h-bar explicitly here, but this is an order h-bar effect. So this is a purely quantum gravitational effect. You can see it's independent of C1, C2, C3, but it is dependent on alpha, beta, and gamma. This specific coefficient 3/5 depends on the density profile. So this value 3/5 is if you choose a constant density profile for the dust ball. But if I make any modification to the density profile of the dust ball, I will get a different value here for this numerical value for this coefficient. So if you had an experimental setup outside the black hole and you could measure, so this is a 1 over r to the 5th potential. You could measure the strength of the 1 over r to the 5th potential outside the black hole, which is due to these quantum hair effects. You could then deduce the density profile of the original dust ball that collapsed to form the black hole. So that's a concrete example of information available outside the horizon about the internal state of the black hole. Okay, so 100% in contradiction to what is normally said about the classical properties of the horizon, classical hair. Okay? Okay, so now let's suppose we want to study the evaporation of a black hole. And let's suppose we want to describe it in terms of amplitude. So I have a certain amplitude to emit the first quantum. So R1 is the first Hawking radiation quantum that's emitted. There's some amplitude for emitting it. This is the quantum state of my black hole. It's some sum over different energy eigenstates of the black hole. And let's suppose this amplitude to emit a Hawking quantum with quantum numbers R1 is a function both of the state of the black hole En, and the state of the specific quantum numbers of the quantum that's emitted. Okay? So you would write this exact formula if, for example, you just had some really complicated atom, and this very complicated atom could emit radiation. You would write a set of amplitudes like this. So this initial state evolves into this state, and I have to sum over the possible states of the emitted quantum. So that's this quantum number R1, I have to sum over that. And I also have to sum over all the different energy eigenstates that are in this original semi-classical description of the black hole. Okay? And these CNs specify the actual state of the black hole. So I have a black hole in an initial state, which is specified by these CNs. And when it emits the first quantum, This is the description, okay? It's very straightforward, actually. It's kind of complicated in terms of notation, but it's very straightforward what's happening here. I emit a mode, the black hole loses a little bit of energy, delta 1 is the energy of this mode, and this is the amplitude for that to happen, okay? But let's just repeat this now. So now let's suppose I emit the second mode. The final state of my black hole will be a sum with these coefficients Cn of different black hole states where it lost delta 1 and delta 2 of energy, and then heading off to asymptotic infinity, I have these two states, R1 and R2. Okay? And now I have a product of these two amplitudes. The amplitude I had originally to emit the first quantum, and then the amplitude to emit the second quantum, but importantly, the amplitude to emit the second quantum depends on delta 1, the energy of the first quantum. So this is causing entanglement across all of these states. So we have a very complicated sum over these states, okay? And the fact that this alpha for emission of particle 2 depends on what happened in particle 1 causes entanglement, okay? So now let's suppose I've emitted all of my quanta, so I have now this final state. And if you look at this, this is that general basis state that I introduced at the beginning of the talk for the radiation, which is finally heading out to infinity, and there's no more black hole, okay? Now what do we care about? Well, we have this very complicated product of alphas, and because the alpha to emit the nth mode depends on what this should be 3. Okay, this should, no, that's fine, that's right, sorry, I don't have all these on here. But each of the alphas depends on what happened in the previous step, okay? And so you can see this is a highly entangled state. It doesn't look anything like the state that's postulated by Matur. If you look at that set of product states, Matur has each emission of a Hawking quantum as being more or less an independent event from the previous emissions. And that's also true of the original Hawking calculation. But it's not true actually once you know that there's quantum hair. Once you know that the external state of the black hole knows what happened before. In fact, it knows how the energy of the black hole changed. And that quantum hair affects the next amplitude. Then you get this highly entangled state. Okay? And this highly entangled state has that property that those values of x, those entanglements, are spread uniformly over that whole Hilbert space. Okay? Now, this is actually the state of the radiation. So the fundamental question in the Hawking problem is if I gave you the radiation state at late times, could you invert and come all the way back and tell me what the quantum state of my original black hole was? And that boils down to extracting these C's, right? So the black hole state is basically just determined by the values of these CNs. But you can see that if you made enough measurements, if you had the ability to measure this radiation, this whole thing, this whole radiation state very, very carefully, these alphas are in principle calculable. We can't actually calculate them, but in principle they're calculated from known physics. So this coefficient function is known. This is a known basis. So in principle, if I made arbitrarily precise measurements of this final radiation state, I could deduce these values Cn, and then I would know the initial state of my black hole before it started evaporating. So this is, because it's quantum mechanics, this is an invertible process. It's a unitary evolution. The evolution from here to here is manifestly unitary. And so there isn't a case where I have a pure state and then here I have a mixed state. I have a pure state and it evolves to another very complicated pure state. And so I would claim this is actually the resolution of the Hawking paradox, that these widespread entanglements are what allow the page curve to turn over, and they're also what allows the final state to be pure. Okay? All right, so this is my last slide. So what did I say today? Classical no-hair theorems do not extend to the quantum realm. Quantum state of the gravity field, which is really the geometry outside the black hole, carries information about the interior state. This is not true in the lowest order Hawking approximation, but it's true once you introduce even the simplest quantum mechanical effects for the graviton. Taking this into account, we can describe unitary black hole evaporation in terms of these amplitudes alpha. The alphas only have to deviate very slightly from the Hawking results. Okay, they just have to deviate very, very slightly, but they still spread entanglement throughout the Hilbert space. The final radiation state is a complex macroscopic superposition state. This is also reflected in the density matrix that you get from the replica wormhole calculations. All of the formulations of the paradox are given on a specific spacetime background. They do not, they do not consider entanglement between different spacetime geometries. Okay, so let me stop there.
Question.
So you don't think the firewall picture is correct?
Yes, I can come back to that. Yeah, so if you're the people who did the replica wormhole calculation, like say you're Maldacena, okay? And you say, hey, you know what, we did this toy model, it's only a toy model, but we think it really does tell us something about real black hole physics. And yes, pure state evolves to pure state. Or at least it looks that way because we can at least compute this part of the page curve, okay? But if you're Juan and you still believe in the firewall argument, then you have to say, well, I don't know how this happened. Something very strange must be happening in order that I solve the Hawking paradox. Because somebody proved that you can't solve the Hawking paradox. That's what this supposedly says. This supposedly says you can't solve the Hawking paradox. You either need very strong non-locality across the horizon, or you need a firewall to appear. And I'll explain what that is. So I think the mental state of most people who worked on the replica wormhole stuff, at least I actually know this from actually communication with them. They acknowledge that the density matrix in their calculations has this macroscopic superposition state. But they still believe in this. So they still think, like if you read these review articles that Maldacena has written, he claims there must be some weird non-locality or some, maybe the modes here are secretly the same as the modes here. I don't know if you're familiar with that, but there are these very strange ideas that actually it's an illusion that the radiation modes are independent modes. They're actually just like a rewriting of the modes that are inside the black hole. It's almost philosophy, actually, what they're doing. But I claim that if you go back and you look at the details of, for example, the firewall argument, and you realize that you're dealing with a macroscopic superposition state, you can see that there are loopholes in this argument. So I can go through them if you're interested. It's a little involved because you have to remember how they prove these firewall results. Do you want me to go through it or?
Maybe not now.
Not now. Okay. A wise decision. Yes.
If I understand correctly, your perspective, say, you consider the radiation of different momentum and different macrostates is also applied to normal, say, a box and a box of gas.
Yes.
I think it do not need any spatial property of black hole.
Yes. I like your question. And in the longer version of this talk, oh, do I have no, I don't have that diagram here. Okay, sorry. I thought I had it in my extra slides. There's a very old theorem that was proved by von Neumann in the 1930s, and it's called the quantum ergodic theorem. Okay? It's very obscure. And in fact, the quantum ergodic theorem was only in German for many, many years. And about 10, 15 years ago, people who were doing work in quantum information theory got interested in this particular question. And some people discovered the von Neumann paper, and then they translated it to English. But it was only translated to English around 2010 or 2011, the 2010s, okay? The quantum ergodic theorem can be used to prove the following theorem, okay, as an application. So imagine I have a box, and in the box I have a bunch of little particles, and then I have one big thing. So okay, I have a ball and I have some air atoms, and the air atoms are just random walking or something. Okay, but suppose I want to describe the whole quantum state of the box, some many body system with one single wave function. Okay, I should be able to do that. I mean, we're trying to do that with the black hole. Okay, you can apply the von Neumann-Ergodic theorem to prove that setup will evolve into a macroscopic superposition state where the ball itself has random walked into all possible positions inside the box. And so so you can actually prove this rigorously. So you start out with a Hamiltonian describing the individual small particles and then this ball, and then you can prove that the way this will evolve at late times will look like a superposition of ball at point 1, region 1, coordinate 1, ball at x2, ball at x3, and it's actually a superposition. And each of these states is macroscopically different. And when the ball is at x1, because the small atoms are not allowed to be in the region where the ball is, the coordinate of the big ball is reflected actually in the environmental state of the smaller molecules. And so you can show that the actual Schrodinger evolution of that initial data gives you that macroscopic superposition state. So that's completely independent of black holes, but that's a known result.
So here I'm just wondering, so in the very beginning, it seems your talk includes two parts.
Yes.
It's related to the black hole recoiling.
Yes.
And then you have explanation in many states. Eventually you can explain the page curve.
Yeah.
But the second part is related to quantum here.
Yes.
But at the end of quantum here, you also mentioned the black hole unitary evolution.
Yes.
Just this something like showing the equation from this state to this state.
Yes. Yes.
So here I'm just wondering, this two part is the picture for these two parts are consistent with each other.
Yes.
Would you please?
Yeah. Great question. So I'm sorry if the talk seems confusing, because in a way I'm covering a lot of material. Okay. Most of the talk, the beginning, is this paper, which is mainly focused on the replica wormhole calculation and connecting it to this earlier calculation where I talked about how do you take a maximally mixed state and then perturb it so it's pure, okay? And what we're observing, which I think the replica wormhole people themselves did not realize until we told them, but now they agree with us, that in their calculation is this conclusion about macroscopic superposition states. And they acknowledge that that's true now. But that part of the talk is just explaining to you that if you can find a way to spread entanglement over the entire exponentially large Hilbert space, you have the potential of only introducing really small corrections, so each x is very small, but the totality of them, the effect of them on trace rho squared, can be order 1. Can take trace rho squared from 1 over d all the way up to something approaching 1. Because that was sort of the first part of the talk, and that's basically what's in this paper. Okay. But separately, all this work we did on quantum hair also suggests that yes, you can directly see the spread of entanglement. So these products of alphas are spreading entanglement throughout this very large Hilbert space. The entire Hilbert space of R1 through Rn, you can see the entanglement spreading all the way through it. So the two are connected in that way, but they're very different because the calculation just, this general calculation just talking about density matrices, this is totally general. This is totally general. This could be anything. And at the time these papers were written, we had no idea what was causing X. Okay, it could be stringy corrections, right? Then, in a Euclidean path integral context, they were able to find exactly realizations of this X effect. And we're just pointing that out. Okay, so there are a lot of non-trivial chains of logic in this talk. I apologize, but I'm just, since I'm only in China every once in a while, I try to cover everything. So, yeah.
So any more questions? If there's no more questions, let's start. Professor Xu again.